This is a tutorial on finding the area under a curve. Before we can talk about finding the area under a curve, let's talk about finding the area of any shape. The easiest shape to find the area of is probably a rectangle. So here we have a rectangle, and how do we find the area of it? Well, we measure the length of this rectangle, and then we measure the width of this rectangle, and we take that measurement of length and that measurement of width and we multiply them together. That will give us our area. Now it's important to realize that if I measure this rectangle in feet for its length and feet for its width, that I'm taking a measurement of feet and I'm multiplying it by a measurement of feet, and that the area will end up having units of feet squared, or square feet. If I measure this length in inches and this width in inches, then my area will end up having the units of inches squared. But to find the area of this rectangle, we just measure the length, then we measure the width, and we multiply those two measurements together. So now let's try finding the area under a curve. And let's start with the most basic curve, a horizontal line. Here I have a horizontal line, y is equal to 8. If I want to find the area underneath this line, well, this line goes on forever, so we're going to have to pick x values to find the area between. Let's pick 0, and let's pick 8. Now if you imagine lines going up from 0 and up from x is equal to 8, then what I've created between those two values of x and our curve, y is equal to 8, is a rectangle. I can find the area of this rectangle because this dimension here, our length, we go from 0 to 8, so this is 8. And then our width here, this is the distance between the line y is equal to 8 and our x-axis, which is the line y is equal to 0. So this dimension is 8. So the area underneath this curve, from where x is equal to 0 and x is equal to 8, is just 8 times 8. And that's 64. So measuring the area under a horizontal line, that's easy. All you got to do is measure the distance from that line to your x-axis, and then however far you wish to travel along the x-axis. Take those two distances and multiply them together, and you'll get the area underneath your curve. But what if our curve wasn't a horizontal line? Here we have a parabola. Finding the area underneath this parabola would be very difficult. It's not a rectangle, it's not a circle, it's not any easily identifiable or measurable shape that we have a formula for to find the area. So if I wanted to find the area underneath this parabola, I'm going to have to estimate it. Now the easiest way to estimate the area underneath this parabola is to say, well, rectangles are easy to take the area of. Let's assume that the area underneath this parabola is basically the same area as a rectangle circumscribed around it. I can find the area of this rectangle. This length here, that's about 10. And this width here, that's about 8.5. The area of this rectangle then, that's approximately equal to 10 times 8.5, or 85. So if the area of this rectangle is 85, then I could say that the area of my parabola, well, that's approximately 85. Now, unfortunately, this estimation that we've done is not a very good estimation notice that there's all this area here and here that's included in the area of the rectangle, but it's not part of the area of this parabola. So this estimation that we've created, where the area underneath this parabola is equal to 85, that number is a little bit high. I'd actually say that the area under this parabola is less than 85. So how do we get a better estimation? Well, if we want to keep our math easy, let's use two rectangles. This blue one is called a circumscribed rectangle because it includes areas outside of our parabola. And this red box is called an inscribed rectangle because it's completely inside our parabola. Now we can say that the area of rectangle 1 and the area of rectangle 2, if we add those two areas together, we'll get an estimation for the area underneath this parabola. This first rectangle, the blue one, it includes all of this area that's not part of the parabola. But rectangle 2 here has all this area that's part of the area of the parabola, but it's not part of the area of the rectangle. So let's say that these two areas here that aren't being included in area 2 are approximately the same as the area that is being included in area 1 that's not part of the parabola. Or this area is approximately the same as these two. Then I can estimate the area underneath this parabola as the total area of A1 and A2. Well, our first rectangle has a length of 5, and it has a width, or a height, of 8.5. So area 1 would be 5 times 8.5. And we would add that to area 2. This rectangle has a width of 4 and a height of 5. So the area of this second rectangle would just be 4 times 5. Now 5 times 8.5, that's 42.5. Add that to 4 times 5, or 20, and we're going to get 62.5. So the total area of both of these rectangles is 62.5. And that means that we can say that the area of our parabola then is approximately 62.5. Notice that this number is a lot less than our previous estimate of 85. So using more rectangles and a combination of circumscribed and inscribed rectangles has probably gotten us a better estimate. Now, if you want an even more accurate estimate of the area underneath this parabola, then just use more rectangles. Here we have lots of very skinny and tall rectangles, and we're using it to estimate the area underneath this parabola. Notice that these rectangles are all inscribed, but because we have so many small little rectangles, there's actually very little area here that's not being included when we add up the areas of all these little rectangles. Now, doing the math for rectangles this small would be very difficult because you'd be adding the area of many, many, many rectangles. So typically when we use inscribed rectangles, we use inscribed rectangles that have a width of 1. Now if we use inscribed rectangles with a width of 1 to estimate the area underneath this parabola, well, this first rectangle has a height of 5. This second rectangle has a height of approximately 6.5. The third rectangle is approximately 7.75. Our fourth rectangle and our fifth rectangle have heights of, say 8.25. Then we're back down to 7.75, 6.5, and 5. So the area underneath this parabola would be the combined area of all of these different rectangles. The area of our first rectangle, well, that's its height, which is 5, times its width, which is 1. So the area of that rectangle is just 5. Our next rectangle has a height of 6.5 and a width of 1, and that's just equal to 6.5. Our third rectangle here has a height of 7.75 and a width of 1, and that's equal to 7.75. Our next two rectangles have heights of 8.25, and again their widths are just 1, so their areas are 8.25. We have another rectangle with a height of 7.75. Its width is 1, so its area is 7.75. Another rectangle with a height of 6.5 and a width of 1, so its area is 6.5. And then lastly, we have another rectangle with a height of 5 and a width of 1, so its area is 5. This is why it's very common to make rectangles when you estimate the area under a curve that have a width of 1. Because you're always multiplying the length by 1, it makes the math very easy. If you sum up all these areas, you'll find out that this is 55. So using all of these inscribed rectangles with a width of 1, we're going to say that the area underneath this parabola is approximately 55. Notice that this is a lot lower than our previous estimate of 62.5. You can also estimate the area underneath this parabola using circumscribed rectangles. Again, to make math easy, we're going to make all these rectangles have a width of 1. Our first rectangle has a height of 5. This one has a height of approximately 6.75, then 7.75, 8.25. The middle two are 8.5, 8.25, 7.75, 6.75, and then 5. Now all of these have a width of 1, so if we take these heights and multiply it by 1, our area is the same as the height of all of these rectangles. So 5, 6.75, 7.75, 8.25, 8.5, 8.5 again, 8.25, 7.75, 6.75, and 5. Add them all together, and we'll get 72.5. So by using circumscribed rectangles, we're estimating the area underneath this parabola to be approximately 72.5. So notice if you use circumscribed rectangles, your estimation is going to be a little high. If you use inscribed rectangles, your estimation is going to be a little bit low. So why do we have to figure out how to estimate the area underneath the curve? Well, let's try doing this problem, and we can see how this is useful. We have a man driving from Phoenix, Arizona to Los Angeles, California. The drive takes 6 hours, and during that time the man's speed varies between 60 and 70 miles per hour. The given graph shows this variation of speed. Notice he's going faster and then slower, faster and then slower. Estimate the distance traveled on the trip. Well, remember when we were finding the area of a rectangle. When we measured it one way, we got feet, and when we measured it the other way, we had feet. and then our area was feet squared. Well, in this problem, our y-axis is miles per hour. And then we're going to multiply this by a measurement of hours. Well, if you take miles per hour and you multiply it by hours, that means the area under this curve is going to be in units of miles. So if we want to estimate the distance traveled on this trip, we can do so just by finding the area underneath this curve, because the area underneath this curve is going to have units of miles, or distance. Now, like before, I'm going to use rectangles that have a width of 1, just to make our math easy. But I'm also going to use a combination of inscribed and circumscribed rectangles. And this is how I'm going to make my rectangles. I'm going to start at my first unit, or 0. I'm going to go up from the x-axis on the line x is equal to 0 until I run into my graph. Once I run into my graph, I'm going to draw a rectangle 1 unit wide. Now I'm at 1 on the x-axis. Now that I'm at 1 on the x-axis, I'm going to go up that line, x is equal to 1, until I run into my graph. And then I'm going to draw my rectangle that's a unit of 1 wide. Now that I'm at 2 on my x-axis, I'm going to go up from 2 on my x-axis until I hit my graph, and then I'm going to draw another rectangle that's 1 unit wide. Now that I'm at 3, once I hit my graph, I'm going to draw another rectangle that's 1 unit wide. Now that I'm at 4, I'm going to draw another rectangle that's 1 unit wide. And now that I'm at 5, once I hit my graph, I'm going to draw another rectangle that's 1 unit wide. Notice I'm using a combination of inscribed and circumscribed rectangles. I'm doing this because I'm hoping that the extra area I get in my circumscribed rectangles will be equal to the area I'm losing in my inscribed rectangles. Now my first rectangle, we'll call this area 1, it has a height of 60. My second rectangle, I'll call area 2, this has a height of 70. My third rectangle, or area 3, I'm going to say that this has a height of approximately 65. My fourth rectangle, or area 4, this has a height of, say, 60. And my last two rectangles appear to have approximately the same height. So area 5 and area 6 would both have a height of, say, 68. Now all of these rectangles have a width of 1. So area 1 is just its height, 60, times its width, which is 1. So its area is 60. Area 2 has a height of 70 and a width of 1, so its area is 70. Area 3 has a height of 65 and its width is 1, so its area is 65. Area 4 has a height of 60 and a width of 1, so its area is just 60. Area 5 has a height of 68 and its width is 1, so its area is 68. And area 6 has a height of 68 and its width is 1, so it has an area of 68. If we add up the areas for all of these 6 rectangles, we get 391. That means the distance between Phoenix and Los Angeles is approximately 391 miles. If you did an internet search for the distance between Phoenix and Los Angeles, it's approximated at 357 miles. So our approximation is a little bit off, but it's actually pretty close. So that's how you can estimate the area under a curve and what that area means. This completes the tutorial on estimating the area under a curve.